Hello everyone, welcome to the class ECE418, the Statistical Signal Processing. This is the first week, Friday's class, and we will study some linear algebra. Here's a textbook, the constant page of the textbook. Yeah, here, linear algebra, section 2.3, linear algebra. So we will go over this part. Not just today, we need several days to study the material here. Alright. The basic thing about this part you should already have in your linear algebra course, but we have some advanced topic here. Alright. So ECE418. This is the first week, Friday's class. And then the topic is linear algebra. The first one here, we will know what is a vector. Vector. Now we have two kind of vector: x1, x2 until some xn. This is I say x equal to this, or x equal to x1, x2, xn. So this is a column vector, this is row vector, right? Column vector. And the row vector. So we have two kind of vector. And the second thing is the matrix. Matrix. A matrix, usually we use a capital letter for matrix. It will be, it's a list of numbers in certain row and column. So like A11, A12 to A1n, and there's A21, A22 to A2n until AM1, AM2 until AMN. So this is a M by N matrix. M by N matrix. It has M rows and N columns. So definition is just like this. It's quite simple, right? Then we consider some operation on them. Operations on vectors and the matrix. The first one, of course, is a plus. Here's we have requirement same size, and then we do element by element. Element by element. I use example to explain. First example, we can have 1, 2 plus 1, 3 equal to, you see, we have two column vector, and size are same, right? 2. So element by element do summation. So 1 plus 1, I get 2. 2 plus 3, I get 5. Right? So element by element. And the second one we consider 1, 2 plus 1, 2, 3 equal to what? Nothing, right? The size is different. No answer, right? There's no answer. We cannot do the summation when they have different size. Like the third one, I have 1, 2, 3 plus 2, 2, 2 equal to, okay, same size. Right? Then element by element, I have 3, 4, 5. Okay, So we can do this kind of summation, right? The first one, if they have different size, different dimensional, 1 plus 2, 1 2 and 1 1, this one still no answer, right? One is a column, one is a row. You cannot do summation on that. These are vectors. Yeah. And the matrix are same thing. Matrix 1 2 3 4. I gave the 5s. 1 2 2 2 plus 1 1 negative 1 negative 1. I have two matrix, right? Both are 2 by 2. 2 by 2, right? 2 rows, 2 columns, same size. So we can do the summation element by element. So 1 plus 1 I get 2. 2 plus 1 I get 3. 2 minus 1 I get 1. 2 minus 1 I get 1 again. Okay, so we can do the summation like this. If the size are different, you cannot do the summation. You cannot do the summation. And here we can consider, the matrix, the vectors as matrix. So like 1 and 2, some point you should know. This is a matrix of size. Now we have this is 2 1, 2 rows and 1 column, just size 2 and 1, or 2 times 1. Same meaning. Yeah. So you can consider vector is a matrix, or like 1 1 6. This is a matrix of size. Now is 1 row times 3 columns. Yeah. Alright. So this is a operation. You can just consider all of them, they are vectors. Even their column or row vectors, they are also kind of matrix. Right? This is summation. Second operation, subtract. That is same way as the plus. Same thing. You just if they are same size, you can do this operation element by element. If they are not in the same size, then you can't do that. Okay. This is first one is summation. Second one is subtract, and the third one is a multiplication. Times. For matrix, we want like this: row times column. Column. Row times column, element by element. And then do a sum, do a summation. Things like this. I start from vectors. Vector 1 3 4 times 1 1 1. Okay, for simple. We do it. This is this row vector, this is column vector. I can times them together. Row times column, element by element, and do summation. So 1 times 1, element by element. 3 times 1, and 4 times 1, and then do summation. I can get one number. This is a 1 is 1, 3 or 1 3 4. It's 8. Okay, it's like this. Okay, then we can extend these to larger size, different size. Like 1 1 1 1 2 3 times 1 negative 1 1. Like this. Okay, I can consider this is one row, this is a column, this is another row, another same column, right? So I can use the first row times this column. I can have the element 1 times 1 plus 1 times -1 plus 1 times 1, okay, times them element by element, then do summation. This is the first number. Second number, similar thing, 1 times 1 plus 2 times -1 plus 3 times 1. Okay, I put them like this. Then these give us to summation 1 is 1, minus 1 and plus 1 again, this is 1. 1 minus 2 plus 3, I got 0, right? No, 1 minus 1 is -1 plus 3 is 2. Okay, I got this. Alright, so you need what? You need the row in the size of rows in the first matrix had the same size of the columns in the second matrix. Then you can do the multiplication. In general, A n times m times b with size m times k equal to a matrix C with size n times k. And the element, the ij's element of C is Cij equal to ai1 plus b1j times, and plus ai2 times b2j plus until this is aim the I row m column, right, times this is a b m j, like this. Makes sense? This is formula. Now you look at here, this the Cij, here's the C. This is C11, the first element. There we use the first row of A and the first column of B. The result is the first element of C. Okay, it's like this. And the element, this is A and this is B. A times B. And A, you use the same row. So here's ith row. So I1, I2, Im. They are the ith row. And here's B, element from B, use the same column. So the j's column j, so 1j, 2j until mj. And the second index is the location of the column, right? Same column, so same j. So the row of a row of A and a row of B, you get an element of C. I use a graph to show it. Like this. This is A size n by m. So we have n row and m column. And this is B. The size is m times k. So m row, k columns. And the result, this is multiplication. Result, we get C. Here's n. Here's a k. Here's a k. And one of the element, like here, this is C. See, the size is n times k. Here's n times m and m times k. After you times these two together, it seems like this m cancel. You have n and k. And suppose this is the ith row, and here's a j's column. Then this element is Cij. The Cij, what is Cij? Cij is, this is A, this is B. You choose the ith row from here. You choose element from this row, and jth column, you have an element here, then times them element by element. So Cij equal to A, the ith row. Now I can use a shorter notation. A ith row with a k is running k from n to m, and times b, the k j, the kth element of row j, the jth row, the same k run from 1 to m into this one. Okay, so you can have the element Cij like this way. Okay, check example, more example. I have 1 2 3 1 1 1 times 1 1 negative 1 negative 1 2 1 0 1 0. Like I have two matrices. The first one is 2 by 3, and second one is 3 by 3. This is A, this is B. Then C equal to A times B, or have size 2 by 3 size. Right, size is 2 by 3, and its element, I need 2 rows and 3 elements. The first element, this one, you will pick the first row and first column for this element. So I have 1 1, and 1 1 is 1, 2 negative 3 is negative 2, 3 times 0 is 0. So I have 1 minus 2, I have negative 1. And second element, this one, this element, we use the same row of A but the second column of B. I have 1 times 1 plus 2 times 2 plus 3 times 1. So I have 1 and 4 and 3. 1 and 4 is 5, and 3 is A. Now we can do the similar calculation. Alright, I leave it here. If you are interested, you can finish all this element same way. Like this element, this is the second row, third column. Right, this is C2 3. Then you check the second row of A and third column of B, element by element, do summation. Then you can have this value. Alright, yeah, this is a kind of calculation. You have a lot. You see, you say it's a multiplication of 2 numbers, but actually you need a lot of multiplication and summation. Now, depending on the size. If the size is large, that will be a lot of work. Okay, but we can do this kind of things. Use computer. Yeah, later I will show you. Okay, so this is operations on matrix. We have third one, summation is the first, the second one is subtract, the third one is multiplication, and the fourth one, inner product. Product of matrix, of vector. This is just for vector, not for matrix, just for vector. We suppose 2 vectors, they are same size. V equal to V U, 2 vector, same size. Then V and U do inner product. The notation is like this: U and V with one large, one small. Yeah, so this means inner product, or equal to V1 times U1 plus V2 times U2 plus until Vn times Un. It's an inner product. This is just for vector inner product. For inner product, we have a special case. V and V itself, special case. V and V do inner product. Same vector do inner product. There will be V1 square plus V2 square plus until Vn square. Same size n. Same size n. So it is square root, right? It's a square summation of the squares. You can think it's like if this is a signal, if V is a kind of signal, this will be power, right? You can think this is power. And if you take square root, you will get a length. Square root of V equal to square root of V1 square until Vn square. This is the length of V, and denoted as V, like this. Yeah, we use it's kind of absolute value, but not really absolute value, right? If the vector has size 1, there will be just one number, right? One number. Then here is just V1 square. Square root of V1 square. That is just the absolute value of V, right? Like 2 take square, you get 4. Then square root, you go back to 2. Negative 2, you take square, you get 4. Take square root, you get 2, which is a negative 2. Remove the negative, right? So it's absolute value. This one, in one-dimensional case, this is just absolute value. In high-dimensional, this will be length of V. Make sense? We can try for two-dimensional case. V equal to V1, V2. We can represent it in a graph in this way. V1, V2. And here's a point V. This is V. And the length, this one. This is V1 square plus V2 square take square root, right? We know this is a law, right? This is a law. It's a long history. We know this, right? The length of this just V1 square plus V2 square. You get square root. Take square root. Then we have the length. So this one is the length of V. For high dimensional, this is also length of V. Yeah, you need some imaginary for high dimensional. 2-dimensional is fine. 3-dimensional is also fine. High dimensional, we use the same notation, same meaning. We call it the length of a vector. Right. So we have these 4 kind of operations on the matrix. Okay. Then for the multiplication, then we can have the inverse, right? Phi, the inverse matrix. This is just for matrix, for n by n square matrix. For n by n for square matrix, A inverse equal to what? A inverse is a matrix. I say so that A inverse is a matrix, right? I use A inverse times A, I will get 1, 1. All the other elements are zeros. N by n. It's a unit matrix. The vector, the matrix, all the number in the diagonal is 1 and all the other elements are zeros. So this is a unit matrix. Unit matrix. If A times A inverse times A, you get this one. And also A times this A inverse is also unit 1. So this one is called the inverse of matrix. Similar with the inverse of number. right? We can have multiplication. We can times two matrices together. We can A times B, we can get a C. If A times something, make this is a unit matrix, which is this one, then this B is the inverse of A. Right? Similar with number, but of course it's more complex than number. And for this is it's a hard calculation to determine what is A inverse. But for second order, we can have a formula to do it. But before that, we need another thing, which will be used in the calculation of the inverse matrix. That is a 6 determinant of A with size n by n. This one actually A n by n is a A11 times, okay, how to say, I will see determinant is A11 times the determinant. I say this is I need a notation. I use A hat 11. What is A hat 11? Like this is A with size n by n. Then this element, this is A11, the first row, first column we have element. Now I remove the row and the column. Start from this A11, I have one row, one column. I remove, then the rest part. Okay, the whole thing is A n by n, and this part I use A hat 11. A hat 11 size n minus 1 times n minus 1. So it's a smaller matrix. We remove first row, first column. I have a smaller matrix. This is A11. And minus A12. A12 is here. This is A12. And times determinant of A hat 12. What is A hat 12? We do the same thing. This one, this is a A12. And then I remove this row and this column. I have the rest part and this part, right? The first row, first column, I have some element here. Then all the element in the shadow, I put them together. I get a 12 hat. This is also smaller size. Smaller size. Okay, we do the same thing. The first element, second element, then the third one. Now it's plus A13 times the determinant of that A hat 1 1 1 2 1 3. Right, third one is 1 3. Then minus and so on until the last element. It's plus or minus, that depends. The first one is positive, then minus, then plus, then minus, one plus, until the last element. So the last one will be plus or minus. That depends the length of odd or even, depending on the n, right? Times this element A, first row, the last element, times the determinant of that A hat. It's kind of a rest part of this matrix, right? We remove one row, one column. I have the rest part. This is a 1 n hat. Okay, this is the definition. What is the determinant of n by n matrix? We can calculate it by this way. And then we need the determinant again. This determinant, they are for some smaller size matrix. Okay, then how to calculate this one? Use the same formula. It is a summation with more terms which has even smaller size matrix until the last one. For if A equal to just one element, then the determinant of A is just A. So we have two formula. We combine these two, then we can calculate the determinant of any matrix. You got it? Yeah. Okay. Then after we get the determinant, then we can have the inverse matrix. So go back to inverse matrix. Not all. I just gave the 2 by 2 matrix. 7. A inverse for A with size 2 by 2. Like A equal to, suppose A is some matrix 2 by 2. I say A, B, C, D for element, right? Then what is A inverse? It will be 1 over determinant of A times, here's D, here's A, here's negative B, here's negative C. That's it. Here, of course, you should know what is the determinant of A. Here, determinant of A is, no, this is A, right? This is A. Then by the definition, we need to use the first element A times the rest part. Now rest part is just D. So it is A times D. Then second term is this element B times the rest part. You remove row and column, you have a C left, so times C. First element you need a positive, second you need a subtract. Okay, this is determinant of A, where A is this one, 2 by 2 matrix. So A times D minus B times C. Yeah. Like if you give a cross here, the row looks like this: A times D minus B times C. So this is the determinant of this A. And this part you need to change the element. A and D, you change the location of these two. Move D to the top and A to the bottom. So you have D and A. These two elements, B, you need to change the sign on it, and C is also you need to change the sign on it. Now we can do a verify. A times A inverse. What is that? It is A is A, B, C, D, and A inverse is this is an element. This is a constant, not a matrix, right? Just a number. Number times the matrix. You just use this number times every element by element, or you can just leave it. You leave it. You put it in the back. It's fine. This is number, and here's a D minus B, negative C, and A. Okay, we can check this. This is the multiplication of two matrices. How to do it? We check the row and the column, right? A, B, and D, C. Times them element by element, then do summation. So this is A, D minus B, C. Then the first row and the second column. I have AB and the negative BA. So I have A times negative B and plus B times A. Okay, this is the second element. And then I use this row and this column. So I have C times D plus negative C times D. So this is CD minus DC. And then the last element, CD and the negative BA, times them element by element. I have negative CB plus positive AD. Alright, this is determinant, which is AD minus BC. Alright, now we do some simplify. This is AD minus BC. This is also AD minus BC, right? This is a number I just times inside the matrix. So this number times first, I get 1. And second, negative AB plus BA. What is this? It's a 0, right? It's a negative AB plus positive AB, right? It's a 0. 0 divided by this, okay, it's nothing, still 0. Here, CD minus DC, 0 again, right? 0 again. And here, negative CB plus AD. It is same, right? Same with AD minus BC. AD minus BC. So this one times this one, I get 1 again. You see? A times A inverse, I get unit matrix. This is a unit matrix. 2 by 2. 2 by 2 unit matrix. If you want, you can use the notation I2. Now I means unit matrix, identical, things like that. Yeah. Alright. So for 2 by 2 matrix, you want to find the inverse, just follow this formula. For larger size, and that will be complex, I do not have formula for you, but you can use computer to do it. Like in MATLAB, we have some built-in functions which include the determinant of a matrix and the inverse of a matrix. We can calculate. We can use MATLAB to find them. All right. Okay. These are the. Let me see. I have the matrix. 7 different way of operations. Okay. Now we consider some useful notation, useful topic we need to use in the later. Okay. You see, when a matrix times a vector A times B, what will be this one? This is A has size like n times m, and B has size m by 1, I times m times 1. The result I denoted as C. I denoted as C. Denote the result as C. I use C to denote. Then when we do this kind of calculation, how to understand it? What will happen? What will happen? We consider special case. N equal to m equal to 1. Special case. So A just one number, B is also just number, C is also number. So this is just a multiplication of numbers. But we consider it in a in a bunch way. We do this for all B's, and what will be C? Okay. This space of B, that is one dimensional. So B could be any number here, any number. This is means the real number, right? This is space of B, and this side space of C. Okay, so here like this is 1, 2, 3. Then times A, you will have A, 2A, 3A, right? Depending on the value, if A, like this A is a larger number, then you will move these three numbers become larger, and if A is capital A is a small number, you will make them smaller. And if A is negative, this is a positive case. If A is negative, 0 is here, then you have A, 2A, and 3A will be here. If A is negative value, this is A smaller than 0. This is another case, right? When A is negative. So here's a time A times B. A times B, you get this one. Now we have high dimensional. If n, m, they are larger size. So here we have some how to say, I just write like this. This is a space of B is m dimensional. B is m dimensional, right? I have m element, so this is m dimensional. And this side we have a space of C is n dimensional, right? It will be n times this n by m by 1, then the result will be C will be n by 1, right? N by 1, you times it together, you get n by 1. So this is a n dimensional, and A times B, right? So here you have an element, then times A you have another element. If this, for example, here I have 4 elements, the forms like a rectangle, square, like square. Then go to here, it's still 4 points, but your location may change, so it looks like, maybe looks like this. Yeah, it's just kind of twisted. Similar with here, this is a times A, so it's like a stretch or press them together, right? Extension or press them together, or reverse way, depending on the value of A. And this one do similar thing. This matrix A will change those B's to here to get some C's, but the location where, you can think it's some object here, you were twisted, and maybe the size also different and twisted, and then go to this side. So this is A times B, you'll get this one. You get this one. Alright. Okay. And then we can have some special vector. This is the second. It's n larger than 1, m larger than 1. We have this. And special case, third case, if a b equal to lambda b, where lambda is a constant, not a vector, it's constant. So what will happen? This case, because now this side, this should be C, right? C size m by 1, right? This is a size m by 1, and this is m by m, right? m by 1. This is m by 1, but B is m by 1, right? We know B is m by 1, so this is also m by 1. So in this case, we need n equal to m. So that means A is a square matrix, m by n, and the B size is n by 1. This is n by n, this is n by 1. So the size A will be a square matrix, and B is a vector with same size with A, and its result is also B times a constant. So the things like here you have a B, you suppose you have some, like maybe even more excess. Here just suppose 3 excess. This is B. Then this side, A times B will be lambda times B. This is B, lambda times B. Here's A times B. You will get this one. The vector where you just change the length of this B, but the direction, they are same direction. In generally, when you times a matrix A on a vector, the result, usually it will you will have some kind of twisted. They want to keep the same direction. But this is special case. If we have this one, okay. If this one, right? I'm talking all of this is explain what is the meaning of this formula. of this equation. If we have this, if a b equal to lambda b, we call b is an eigenvalue, eigenvector of a with eigenvalue lambda. Okay, here A must be a square matrix. This is a condition. A must be a square matrix, and B should be a size n vector. This is the eigenvector and eigenvalue. Eigenvector and eigenvalue. Now, how to find the eigenvector and eigenvalue? Actually, here, this is a kind of equation. Lambda and b, they are unknown. A is given. You can solve it. You will say, okay, this is just one equation, but I have two unknowns, lambda and b. How to solve it? But actually, this is not just one equation, because this is a matrix times a vector equal to another vector. If you compare both sides element by element, you have more than one equation. You have several equations. So you can solve it. You can always find a solution for this one. You can find the lambda and the b. You just solve it. Alright. These are the eigenvalue. This is one thing. Eigenvalue and eigenvector. Alright. And another thing we need to use is, okay, this is a times b. What is a times b? One matrix times a vector. Okay, now if a times x, what is this? What will happen? What will be the result? What will be the result? Here's a is, for example, I use a matrix example to say. Example. 1, 2, 3, 4, a square matrix times x1, x2. What is this? This is 1 times x1 plus 2x2. Here's 3x1 plus 4x2. You see? And one more. 1, 2, 3, 2, 2, negative 1 times x1, x2, x3. It will be x1 plus 2x2 plus 3x3. And here's 2x1 plus 2x2 minus x3. Okay, so when we use a matrix times x, a list of some unknown variables, then we will have a list of kind of part of an equation, the linear combination of the unknowns. We have this. So this way give us a method to represent a list of equations in a matrix way. So like 1, 2, 3, 4 times x1, x2 equal to 1, 1. This equivalent with 1 times x1 plus 2 times x2 equal to 1, and 3x1 plus 4x2 equal to 1. Right. So this one equivalent with this one. Got it? So we can, if we have several equations looks like this, we can represent in a matrix way. Alright. So this is one thing. Another thing is, if I have x t times x times x. So what is this? What is this? Here, xt means transpose. Transpose of x. For example, x1, x2, x3 transpose equal to x1, x2, x3, right? We just change the size, change the line in the row, and the 1 and the 2 transpose is 2, 1. Is 1, 2, still 1, 2, but the row turned to be column. Yeah, you can switch row vector and the column vector by a t. In MATLAB, xt in MATLAB is x prime. Now what is this one? Okay, example. We can have x1, x2 times 1, 3, negative 1, 4, for example. Here's x1, x2. What it is? Okay, we do multiplication. We use a row times a column. So this is x1 minus x2. Use a row and a column. I have 3x1 plus 4x2. And here's x1, x2. And then element by element. The first row times this column, I have x1 squared minus x2 times x1. x2 times x1. And the second element and the second element. This is a 3x1 x2 plus 4x2 squared. And then do summation, right? Element by element, do multiplication, and then add them together. Result is x1 squared minus 1 plus 3, so it's a plus 2 x1 x2, right? x1 x2 x2 x1, they're same. The last one is 4x2 squared. So what is the result? The result is it's a summation with those variables x1, x2. Each term is a second order, right? x1 squared, x2 squared, or x1 times x2. It is still second order. So all the terms, there are some second order terms. And with coefficient, here's 1, here's 2, here's 3, here's 4. Where does the coefficient come from? You see, 1 is this one. This is 1. And 4 is here. And this 2 is 3 minus 1. You get 2. Okay. Actually, it's 3 minus 1. Right? So this one, you can just by observe to get the result. This one times square of x1. This one's the square of x2. And this is x1 times x2. This is also x1 times x2. And combine this together, you get positive 2, right? Negative 1 plus 3, you get 2. You get this one. Okay, this kind of things we call it quadratic form. Quadratic form. Quadratic form. So this is a quadratic form. We will use this one in a lot of places. When we have a summation with some variables here, I just give x1, x2. Maybe you have more, like x1, x2, x3, x4 until x10. Then you have a long summation with a lot of second order terms. You can try to write it in a matrix way. It is just like this, with certain certain matrix A. Alright. Okay, that's all for today. Let's see you next time. I have a little bit over the time. Okay, bye bye. Have a it's Friday. Have a good weekend.